So we're going to go back to the earlier expression for the many-body state expressed in this manner, psi I for the first particle, and then psi j for the second particle. And these mixing coefficients can be just about anything. So if each particle is within some kind of two-level system, then the whole thing is direct product of a two-level times two-level system. So altogether, these coefficients form a matrix A11, maybe I should say A01. Well, it doesn't matter. A00, A01, A10, A11. Okay? And this matrix can be anything. It does not have to be Hermitian. And all these coefficients can be some arbitrary complex number with no relations between them. So the techniques of singular value decomposition is what allow us to decompose even this arbitrary matrix into some sort of organized form. Okay, so what SUV taught us is that I can decompose this arbitrary matrix of coefficients into a product of two unitary matrices, U and V, and with the some diagonal elements, with some diagonal matrix sandwiched in the middle. And the noticeable thing about this is that diagonal elements are all positive, or at least non-negative. Okay, so in terms of the elements, then what this decomposition is telling us is that these elements Aij is Uik, sigma KL, and V dagger Lj. However, this is entirely diagonal, so I can write this thing as Sk times delta KL. And Hermitian conjugate of a matrix has elements which is V star J L. Okay, so then let's see how this whole thing simplifies. There's Sk, and then there's Uik, and then you have to compile this delta function with this V matrix. So then I'm gonna find V star JK. Okay, so since the K's appear 3 times, maybe I should put a summation sign explicitly here because the Einstein convention does not apply anymore. And again, it's let's keep in mind that all of these numbers as k are non-negative. All right, so now we can substitute this expression into the many-body wave function over here. And after some cleaning up, we find the following. The state, which is an arbitrary state for a two-particle system, is written in this way. Okay. All right. So this whole thing represents the quantum state of a particle 1. And this whole thing represents the quantum state of particle 2. Okay, so let me see if I can put this into some simplified notation. So this index I is getting summed over, and so is this index j. It's also getting summed over. So what's left over is some state which depends on this index k, and what's left over from here is also some state that's only depend on k. Okay, so altogether we have an kind of a decomposition of a state, which is an arbitrary state, into this form. So psi k becomes a sum over k, sk, lk, rk. Okay, so why do I introduce this left and right notation? So what I'm assuming is that I have this kind of separation of space where this left space is being occupied by particle 1, and this right space is occupied by particle number 2. So LK represents some sort of a wave function which is localized on this left-hand side of the space. And here the RK represents some sort of state or wave function localized on the right-hand side of the overall space. And what I'm doing is just taking the product of this wave function with the wave function over here. But the key thing is that it's not just one state from the left side and one state from the right-hand side that gets multiplied. In the case of a two-level system, this k should run from 1 to 2. So the decomposition, when I write it out, becomes this. Okay, so if you look at this alone, then this is a product state. And this alone is a product state. However, all of these combined is not a product state. Okay. So finally, we have found a very simple and consistent way of telling whether a state, which is represented by some complex set of coefficients, aij, is separable, therefore unentangled, or not separable, therefore entangled. It's separable or unentangled if and only if more than one of these singular values is non-zero. And it's entangled. Yeah, I'm getting confused. Too many negative words. And this is unentangled. That is, it's a product state if only one S is non-zero. Okay, so the point is that if only one of them is, if one of these two numbers is non-zero, for example, S1 is non-zero, but S2 is 0, then I can simply delete this portion. Then, of course, what I have over here is just a product state. Okay, so the lesson that we get from doing a singular value decomposition of a many-body wave function is by looking at these singular values, that is a whole bunch of SKs, we can tell, we know for sure, whether the states were entangled or not. Entangled or not. And so since this is a sort of calculation you can always run for actually any kind of matrix. For example, if instead of having a two-level system, each particle occupies n-level system. Okay, so that the overall wave function is now sum over these n by n dimensional product spaces, psi I1 cross psi j2, and both I and j run from 1 through n, so that the A matrix consisting of aij elements is an n by n matrix. But other than being an n by n matrix, there's no other symmetry relations that define these matrices. But still, this matrix is subject to the singular value decomposition analysis. And when having gone through this analysis, you find that this diagonal matrix has more than one non-zero singular value, then the state is entangled. Because what it means is that it's impossible to put these state into some sort of product form by any rotation of the basis. Okay, so apparently the technique of the singular value decomposition, which was probably invented really long time ago, I guess well in the 19th century, comes into play and plays a critical role in determining the nature of the many-body wave function. In fact, it acts as a criterion for determining whether the many-body state is entangled or not. Okay, so for any sort of many-body state, one can perform this singular value decomposition analysis and put the many-body wave function into this sort of form with a single summation from 1 through n, rather than the double summation over the indices. And this is also known as the Schmidt form of the wave function. And this is something one can do generally. And furthermore, because this normalization has to hold, that means sk square, lk overlap with lk, rk overlap with rk has to be 1. But these are already normalized states, so they're equal to 1 already. So that means the sum of the singular values has to be 1. Okay, so there's an interesting possibility of probability. Yeah, there's an interesting probability of maybe trying to interpret all of these singular values as some sort of probability function. Okay, because the defining characteristic of a probability function is that all of these numbers has to be non-negative and their sum has to be always 1. And these singular values happen to satisfy both of these requirements quite naturally. And so it's extremely tempting to give some sort of probability interpretation to the singular values. Now, one of the ways in which this probability interpretation can be made more formal is by defining a quantity which both in the information theory and also in statistical physics is called the entropy, which is a product of the probability multiplied by the log of the probability summed over all possible events. Okay, and since we're talking about the singular values, pk can be replaced by sk squares. And this quantity is going to offer some sort of measure of entropy of the object. Okay, so in information theory or in statistical physics, entropy measures the degree of disorder or randomness. But clearly, that cannot be what's being measured by this quantity because we're only talking about some quantum wave function. And wave function itself does not have any sense of disorder or randomness. What it measures instead, it's a kind of degree of entanglement. Okay, because for example, if only one of these SKs were equal to 1 and everything else was 0, then the calculation quickly shows that the entropy has to be 0. Okay, so the product state, which by definition has only one of these SKs equal to 1, has this entropy equal to 0. So this is the least entropy, smallest entropy state you can imagine. So on the other hand, if this quantity becomes larger and larger, it means that you're kind of moving the state towards the direction of having more and more entanglement. And in statistical mechanics or information theory, the maximum entropy state is the one where all the probabilities are equal. So if there are n possible outcomes, then each outcome comes with an equal probability of 1 over n. And that's the state with the least amount of information or the most amount of disorder. In that case, the entropy log of p works out to what? Log of n, right? This is something you can easily check. So this is the maximum entropy you can possibly have for a system with n possible outcomes. Now, in a similar way, this quantity where the probability function is being replaced by the singular values will have the maximum entropy of log n if all the singular values were identical. Okay, and we call that situation maximally entangled. In analogy to the situation in statistical physics where this refers to the case of a maximum entropy, this refers to the situation where the wave function has the maximum entanglement between the left-hand side and the right-hand side of the system. Okay, so an example of a maximally entangled state is 0, 1, minus 1, 0. Okay, in fact, using this wave function, you can compute everything. Compute all the singular values and convince yourself that both S1 square and the S2 square are equal to 1/2. And so therefore, if you have this sort of quantum state, then this entropy will have the maximum allowed value of log 2. Okay, so in complete analogy to the word entropy, this quantity is called the entanglement entropy. Entanglement entropy, or simply EE. Because instead of measuring the degree of disorder in the system, it's measuring the degree of entanglement in the system. And there's a whole spectrum of many-body states ranging from 0 entanglement entropy state, which is a product state, to the maximally entangled state, where the entanglement entropy is equal to log of the number of degrees of freedom. Okay, so I should probably leave these calculation of the spectral of the singular values for these state as an exercise. By the way, this is called a spin singlet state, or just a singlet state in the language of a spin. And in the more familiar notation, this is just spin up down minus down up state, which carries the total angular momentum 0. So sorry, this S is not the entropy, but the total spin. Sorry for the confusing overlap of the notation. So this is a spin singlet wave function. And the spin singlet state is in fact one of the most well-known example of a highly entangled state in nature. So when people do experiments on entanglement using actual physical system, they tend to turn to these singlet spins and try to play around with them.